So today we're going to talk about Theorem 10.1. Theorem 10.1 states, a line is tangent to a circle if and only if it is perpendicular to a radius. One important thing to note about this theorem is that it's a biconditional statement, and we know that because it says if and only if. Because this is a biconditional statement, it means that there's really two ways that we can read it. One way to read this theorem would be if P, then Q. This reading would say, if a line is tangent to a circle, then it is perpendicular to a radius. Now, note that in this case, our condition would be we have to have a tangent line. So if we saw a diagram like this, I would have to tell you that this line right here is a tangent line. And this line right here we know has to be a radius just because the way that it's drawn in. It starts at the center of our circle and it goes out to one of the edges. Now, what this theorem says then is that because we know that this is a radius and this is a tangent line and they meet at this point of tangency, this angle right here must be 90 degrees because the two lines will be perpendicular. The second way to read this theorem would be if Q, then P. Note that this statement will also be true. Reading in this direction, it would say, if a line is perpendicular to a radius, then it is tangent to a circle. Now notice that our condition has changed. In this problem, we still know that this line is a radius. That's just by definition. But we no longer know that this line is a tangent. Instead, we are just going to consider this a line. The condition for using this theorem is that these two lines must be perpendicular to each other. So that must be given to us in order to then claim by Theorem 10.1 that this line is indeed a tangent line. So they work sort of backwards from each other. They are slightly different, but they deal with two different types of problems. We'll look at some examples. So if we look at this example right here, it says determine the radius of circle C. Now I should have been a little bit more clear. It should say given AB is tangent to circle C. Determine the radius of circle C. So in this problem, we're going to start with the assumption that this line right here, AB, is a tangent line. We also know that CA is a radius. So by Theorem 10.1 then, we know that this angle right here must be 90 degrees. In order to solve for R now, we're going to use the fact that we have a right triangle here. Now, a very powerful tool that we can always use with, or almost always use with right triangles is the Pythagorean theorem. Now, for a Pythagorean theorem, we know that the side across the 90-degree angle is going to be our C, that is our hypotenuse. The other two sides doesn't really matter. I'm going to call this side A, and I'm going to call this side B right here. So I'm going to plug in Pythagorean theorem is A squared plus B squared equals C squared. One thing to be very careful about is that if we look at our hypotenuse here, the entire hypotenuse is this line CB. The only piece of information that we were given about this line CB is that from the circle to this point B is 18. We were not, however, given the length from C to the circle. Well, one thing that we should notice is that this is also a radius, and we know that the radius inside of the same circle must be exactly the same. So if this radius right here, CA, is R, then this length right here must also be the exact same thing. It's R. So the entire length of this line from C to B is not just 18. The length of that entire line is actually R plus 18. We can add those two chunks together using the segment addition postulate. So to solve this problem then, I'm going to plug in A. A is just R. Plus B, we know is 30, equals to the entire line C is R plus 18, and we're going to square that. From here, it's a whole lot of algebra. It looks nasty, but bear with me, it's not that bad. R squared just stays R squared. 30 squared is 30 times 30, which is 900. And on this right-hand side, this is going to be a little bit of a throwback to algebra. We're going to have to use the distributive property. So I can rewrite r plus 18 squared as r plus 18 times r plus 18. And now we can use the distributive property. I can take the r, multiply it by this r, take this r, multiply it by that 18. That r times r gives me r squared, plus r times 18 is 18r. Then I need to multiply the second term, which is 18 times r, which is 18r, and 18 times 18, which is 324. Notice that I have not done anything to the left side of my equation, so it's still going to just stay r squared plus 900. One thing to note here is we have an r squared here. We also have an r squared here. If we subtract r squared from both sides, these simply cancel out, which is a very nice thing. I'm going to rewrite my next line as just 900 equals to 18r plus 18r. I can combine those like terms to get 36r. Plus 324 comes down as it is. I can subtract 324 from both sides. 900 minus 324 is 576. 36r. I can divide both sides by 36, and that would tell me that r is equal to 16. So, in this circle now, we know that the radius is exactly 16 units. The other example. In this case, we're asked to prove that this line AB is indeed a tangent line. Well, again, one thing that we should notice is that we have another triangle in here, and really what we're going to go back to is the Pythagorean inequalities. The idea would be to show that this is a right triangle, because if this is a right triangle, then this angle CAB, this one right here, is a 90-degree angle. If this is a 90-degree angle, it means that this radius AC and this line AB are perpendicular. Therefore, Theorem 10.1 would tell us that AB is a tangent line. So let's look at how we would do this. For the Pythagorean inequalities, we again label our sides A, B, and C. So I'm going to call this side A, call this side B, and our biggest side must be C. One thing to be careful about again is similar to our last problem, we know that the distance from the circle to B is 2, but we were not given the distance from C to the circle. However, we can note that this is a radius, and this line AC is also a radius, so they must be the same exact length. This length is actually 3, which tells us that the length of that entire line CB is actually 5. Now, using our Pythagorean inequalities, that's when we compare the values of a squared plus b squared to whatever c squared is. So we could see that a squared is 3 squared, b squared is 4 squared. That's 9 plus 16 equals to 25. C squared is just 5 squared, which gives me 25. When we look at this then, we can see that 25 and this 25 are exactly the same value. Therefore, we can say that this triangle is a right triangle. This then tells us that angle CAB is exactly 90 degrees. Therefore, by Theorem 10.1, AB is a tangent to circle C. And there you go.